I will share my file. Okay. Any question from previous parts and previous sections? Okay, any question from previous examples and previous parts? Okay, we continue with a graphical representation of roots and corresponding solutions. As you know, to solve a vibrating system and obtain the response of a vibrating system, we need to solve an ODE. And in this course, and especially in this chapter, we deal with a single degree of freedom system, which the equation of motion for a single degree of freedom system is an order 2 ODE. So we need to solve for homogeneous and non-homogeneous equation. This chapter we mostly deal with the homogeneous solution because we only consider the free vibration of the systems. In the free vibration, when you want to obtain the homogeneous response or the free vibration response, you need to solve an algebraic equation, the characteristic equation of the ODE. And when you solve this equation, you obtain two roots for this equation because this is an ODE from order 2. So the characteristic equations will be from order 2 and it will have two roots. According to the position of the roots, we will discuss the response behavior of the system in this section. And the general form of the solution, as you know, is equal to C1 exponential alpha 1t plus C2 exponential alpha 2t, which alpha 1 and alpha 2 are the roots of the characteristic equation. And they can be real, complex conjugate, or double roots. We will have three options. And in the general form, alpha 1 and alpha 2 can be minus psi omega n plus minus I omega n square root of 1 minus psi squared, which I is a square root of minus 1. And this is a general form. I mean, when you deal with a real number, real roots, here the imaginary part will be 0 and we will have two different real numbers. But we will discuss the case when we have underdamped behavior of the structure, which in the underdamped behavior we will have two imaginary roots, two complex conjugate roots with two imaginary parts. Okay, we can plot the response for different positions. Here, for example, first look at this graph. These points are the roots of the characteristic equation. And here you can see, for example, this one. And each root has a specific imaginary and a specific real part. For example, we can assume that this root, it will have an imaginary, for example, 3, and real part, for example, -1, because as you can see, this is the imaginary axis and the real axis, which is this one. So this point has an imaginary, for example, 3, and it will have a real part with a negative sign, which is, for example, -1. Or for example, this one, the real part is, for example, -3 with the same imaginary as 0.1. For example, if it was the √1 and this is √2, the absolute value of the real part for √2 is more than the absolute value of the real part of point or √1. And if you want to compare, for example, the √1 with this one, which we call it, for example, √3, you can see that the imaginary part of √1 is more than the imaginary part as √3, but the real part of √1 and √3 are equal. And the same scenario is between 2 and this root, for example, we call it 4. This root, it doesn't have any real part. As you can see, this is a imagining, only it has an imagined part, and also this one. But if we call it 5, the imaginary part of 5 is more than this one, which we call it 6. This root, which we call it √7, it has a positive real part and a positive imaginary part. And again, this one, again, it has, which we call it, for example, 8. It has a positive real part and a positive imaginary part, but the imaginary part of √8 is less than 0.7, but with the same real parts. So these points can be considered as the roots of the characteristic equation, and these ones which are located on the real axis, the imaginary part for these roots are 0, but the real part for these two, for example, we call them 9 and 10, the real part for these two roots are negative, but for these two roots are positive. For example, we call them 11. And these roots, again, it's 0. It's the origin, okay? So we will have different roots, and according to the form and the coefficients in your ODE, the roots of the characteristic equations can be located in different points in this area, in imaginary and real axis, and which we call it S area, S plane. In this S plane, according to your coefficients K, M, and C, you can find the roots of the characteristic equations, and these roots can be located any point on this S plane. Now we want to discuss the effect of the position of these roots on your response behavior. As you can see, we have plotted the response for different roots. For example, for this √2, this is the response behavior. For 0.4, this one is the behavior for 0.4, and so on. Or for example, for 0.5, this one is the behavior for root in position 5. This one is the behavior of the response when the root is located at position 7. This is, for example, is for the response behavior when the root its position is at 0.8. So you can see, and now we want to discuss what is the effect of these positions on the response behavior. As you can see, when the roots lying further the left in the S plane, I mean, for example, if you compare 0.2 and 0.1, indicate that the corresponding response decay faster than those associated with roots closer to imaginary. So as I told you, you can see here, you can compare 0.2 and 0.1. When it starts from some initial condition, the 0.2 response, the response associated to 0.2, after 1 and 2, and finally in this cycle, in the third cycle, the response achieved to 0 almost. But for the one, as you can see, here we have 1, 2, 3, 4, 5, and after 5 cycles, the response achieves, the amplitude of the response, in fact, achieves to 0. So you can see that by increasing the distance between the roots and imaginary axis, sorry, the response will, of course, the amplitude of the response decay faster. So this is the first conclusion. Here you can see, so by increasing the absolute value of the real part, of course, when the real part is negative, by increasing the absolute value of the real part, the response will decay faster. The second point is, if the roots have positive real part, the corresponding response will be unstable. What does it mean when we talk about unstable system? It means that the amplitude of the response will increase without any bound. For example, in case 0.7 and 0.8, you can see here in case 7, by increasing the time, the amplitude of the response is increasing, or for 0.8 we have the same. Also for 0.11, since there is however, there is no vibrating motion, but the amplitude of the response, as you can see, is increasing. We have the same scenario for this point, and for this point, because all of them have a positive real part. Okay, so this is two conclusion. And the third one, if the roots lie on the imaginary axis, the corresponding response will be naturally stable. Of course, I will explain what does it mean, naturally stable and unstable and stable. Here, just you can compare the results of roots, for example, position 5 and 7 or 1. You can see the response for 0.5, the amplitude will be remain the same. I mean, it's not decrease nor increase, so it will remain the same, and we call it a system with natural stability. So at 0.5, 6, or this one, which is 0 at origin point, you can see that the response will be remain the same and the amplitude will not change. So in these systems, which the real part is 0 and the roots are located on imaginary axis, the response is called naturally stable. The next conclusion is, if the roots are real, the corresponding response will not oscillate. So here you can see when the roots are located on the real axis in case 9, 10, 11, here when it's on origin point, and this one, you can see that the response will not oscillate, or we don't have any vibrating motion when the real, the imaginary part is 0. The next conclusion is, if the farther the roots lie to the left of the S-plane, the faster the corresponding response decreases. It is somehow it's the same conclusion as the first one. As you can see, by increasing the distance between the roots and imaginary axis, the response will vanish faster. So this is the same as the first conclusion. Okay, so these are some conclusions, and the last one is, when the larger the imaginary part of the roots, the higher the frequency of oscillation of the corresponding response of the system. So this one is related to the frequency. As you know, when you extract the roots of the characteristic equation, The imaginary part will appear in the coefficient of sine and cosine terms. I mean, the response is equal to the exponential of real part times by C1 times by cosine imaginary part times by t plus C2 sine imaginary part times by t. So you can see the imaginary parts will appear in the cosine and sine terms. So it will be to somehow the frequency of your response. So by increasing the imaginary part, you can see that the frequency of the response is increased. For example, you can compare case 1 and case 3. Both of them will decay with the same ratio, but the frequency of case 1 is more than case 3. I mean, if you compare the time of the vanish, you can see, for example, in case 3, after 5 seconds, the response will be 0. In the case 1, again, after 5 seconds, the response will be 0. But during the 5 seconds, we will have 1, 2, 3, 4, 5 cycles. But in case 3, we have, for example, 1, 2, 3 cycles. So the frequency in case 1 is more than case 3. Or if you compare here, case 5 and 6, you can see we have more cycles in the same time in comparison with case 6. So the frequency for case 5 is more than case 6 because the imaginary part or the frequency of 0.5 is more than 6. And the same scenario for 0.7 and 8. If you compare 0.7, here you can see at 0.7, the frequency is more than 0.8. In the same time, we have more cycles in case 7 because the imaginary part is more than 0.8, sorry. So the frequency is more than 0.8. So these are the total conclusions from the position of the roots in the S-plane. So when you want to compare the results and when you see the roots of your characteristic equations, to somehow you can decide that what's the behavior of your system, and you can in fact predict the behavior of your system according to these positions and according to these conclusions. Okay, any question? Is it clear from this part? Any question? Okay. So you can see a direct relation between the mathematical equation and the behavior of your system. I mean, when you change the stiffness in your structure, or when you change the mass or the damping, definitely you will change the coefficient in your governing equations. Consequently, your characteristic equation will be changed. And by changing the characteristic equations, the roots will be changed. And finally, you can change the behavior of your structure. I mean, here you can see by changing the position of roots, which is in your hand, by changing the characteristic of your system, you can change the behavior of your system. For example, here, if you deal with a suspension system in a car, usually and most of the time, we prefer to have a behavior like this. Let me show you here. Mostly we prefer to have a behavior like this because we in a car, usually we the ideal behavior is when we don't have oscillation. So we prefer to have this behavior or this one. So you should try to design a suspension system by changing the stiffness and the damping to achieve to this behavior. So it's in your hand when you want to design a vibrating system for your structure according to your ideal behavior. Sometimes maybe you prefer to have a vibrating motion. For example, this one. Sometimes the vibrating motion is a suitable case for you. For example, now we are working on a harvesting system, which we want to harvest the energy from the ocean waves, and we are designing a vibrating system for our structure to increase the vibration and the amplitude of the vibration of the ocean waves to harvest more energy. So we prefer to design a vibrating system with this behavior. So sometimes we need to increase the vibration, sometimes we need to decrease the vibration. So according to your system and to your goal, you can design a appropriate vibrating system for your structure, and it's in your hand, and you can design the stiffness, you can obtain the stiffness. Sometimes the mass, you can change the mass even, and sometimes you can use the damping to control your vibration. So you can see it's exactly a a direct relation between the mathematical equation and the physical behavior of your system. Okay, we continue with one example. A body vibrating with viscous damping makes 5 complete oscillations per second, and in 50 cycles, its amplitude diminishes to 10%. Determine the logarithmic decrement and the damping ratio. So from this data, from the first part here, when it's mentioned that it makes 5 complete oscillations per second, we can easily obtain the period of the motion. And here from the second part, which is mentioned 50 cycles, after 50 cycles, the amplitude diminishes to 10%, we can obtain the logarithmic decrement, and consequently we can obtain the damping ratio. So easily you can obtain the period, as I told you, because we will have 5 complete oscillations per second. So the period is 1 divided by 5, or 0.2. And the natural frequency can be obtained, of course, the frequency of the damped system, omega d, because this is a system with viscous damping. So it will be a frequency of the damped system. It will be 2 pi divided by the period, which is 0.2. And this is the frequency of the damped system. As you can see, this omega, in fact, is in radian per second. If you want to obtain the omega, or the frequency, in hertz, you need to divide this term by 2 times by pi. So if you want to obtain the frequency of the system in hertz, it will be 31.4 divided by 2 divided by pi. Okay, so this is the frequency. And to obtain the delta, or the logarithmic decrement, according to part 2, we know that after 50 cycles, so here we should use from this equation, because it's not a relation between 2 consecutive cycles. This is the relation between cycles 1 and cycle 51, for example. So we will have 1 divided by m, which m is 50, x1 over x sub m plus 1. It will be decreased by 10%. So it will be, if we assume that in x1 the amplitude is 100%, the amplitude in the 51 cycles is 10. So we can calculate by and simplify this term, which is equal to 0.046. This is the delta, or the logarithmic decrement. And then we can substitute into the equation for the damping ratio. Here, this is the damping ratio as a function of delta, or the logarithmic decrement. You can substitute delta is equal to 0.046 and simplify. And finally, you can see this is an underdamped system, because the Kasai is less than 1. So clear? Any question from this example? Okay. The next example is a viscosity dam system has a stiffness of 5 kilonewton per meter, critical damping constant of 0.2. Here, pay attention, this is the critical damping. In fact, this is C sub C, okay? So it's not C, it's a critical damping constant, and it's equal to 0.2 Newton second per millimeter, and a logarithmic decrement of 2 if the system is given an initial velocity of 1 meter per second. Determine the maximum displacement of the system. So the initial conditions is a velocity of 1 meter per second. Determine the maximum displacement of the system. So we need to obtain the equation of motion for this system. And for this purpose, we can use the given data. We have the stiffness, which is 5,000 Newton per meter. We have C sub C, which was 0.2 Newton second per millimeter, or 200 Newton second per meter. We should convert it into Newton second per meter. So we know that the critical damping constant is equal to 2 times by square root of Km. From this equation, we can obtain M, which is equal to 2 kilogram. The next step, we need to obtain the natural frequency of the system. The natural frequency is equal to a square root of K divided by M. We have K, which is 5,000, divided by 2, which is 2,500. The square root of 2,500 is equal to 50. So the natural frequency is 50 radian per second. And we have the delta, the logarithmic decrement. We can obtain the damping ratio, which is equal to 0.3. This is an underdamped system. And we can obtain also C, which is equal to the damping ratio times by the critical damping constant. The critical damping constant is 200, and the damping ratio is 0.303, and we can calculate the C. Now we can obtain and we can extract, in fact, the equation of motion for this system, which is mx double dot plus cx dot plus kx is equal to 0. Or we can write in the standard form of the equation of motion. Both of them is correct. So you can use the omega n and psi, or the natural frequency and damping ratio, to obtain the governing equation, and that's equal. If you want to use these two terms, we will have x double dot plus 2 psi omega n x dot plus omega n squared x is equal to 0. The response for both of them will be the same. You can check it at home. I mean, you can extract the equation in the standard form and solve it and plot the response and compare with the response for this equation, and you will see both of them will be the same. But the initial condition at t is equal to 0, the displacement is 0, but the velocity is 1 meter per second according to the problem, which is a given data. The next step, we need to solve this equation and obtain the response by using these two initial conditions. Okay, so this is the equation of motion. We need to form the characteristic equation, which is the coefficient of x double dot times by alpha squared, the coefficient of x dot times by alpha, and plus the coefficient of x, which is 5,000. So this is an algebraic equation from order 2. You can easily solve this equation and obtain two roots of this equation. Alpha 1 and alpha 2 are equal to minus 15.16 plus minus 47.6 I. So you can see we have a negative real part. So according to the previous section that we discussed, the system will be stable because the real part is negative. And also we have imaginary part. So when we have imaginary part, it means that we will have an oscillating motion, or we will have a vibrating motion. So the response xt is equal to exponential of real part, which is minus 15.16 times by t, multiplied by c1 times by cosine of imaginary part times by t, which is 47.6, plus c2 times by sine imaginary part times by t. Now we need to obtain c1 and c2 using the initial condition. And the initial condition at t is equal to 0, x must be equal to 0. So here in this equation, we substitute t is equal to 0. It will be exponential of 0, which is 1. c1 times by cosine, here we will have 47.6 times by 0, which is 0. So it will be c1 cosine 0 plus c2 sine 0. And here the sine 0 is 0. So we will have c1 times by cosine 0, which is 1. It will be equal to 0. So c1 is 0. So the first coefficient is 0. So this term is completely removed from the response, and the response is equal to c2 times by exponential minus 15.16t times by sine 47.6t. So this is the response. The next one, initial condition is at t is equal to 0, x dot is equal to 1. So we need to obtain the derivative, or the x dot, or the derivative of x with respect to time. So we will have only c2. It will be the derivative of the exponential term multiplied by sine function plus the derivative of sine function multiplied by exponential term. So we will have this term, and then we substitute t is equal to 0. We will have sine 0. So this term again will be removed. It's 0, but this term is cosine 0. It's 1. So it will be 47.6 times by exponential 0, which is 1. This term is 1, times by c2 times by 1 is equal to 1. So c2 can be obtained, and it's equal to 0.0209. And when you substitute here, you can obtain that the response xt is equal to this term. So this is the response of your system. And if you plot it, you can see the behavior of your system. Also, you can use the formula as I explained. I mean, you can write that xt is equal to this term in sine form. X naught can be obtained from the initial condition. The initial condition for x is 0. So these two terms are 0. V naught is equal to 1. So this is 1. And omega and psi are obtained in previous slide. For phi naught, you can use this term again because x naught is 0. So this term will be 0. So you can see phi naught will be 0. So you can substitute here again. Psi and omega n are obtained from the previous slide, okay, in the first section of this example. So you can use this equation, and you will see you can extract the same result. But always I suggest you to use this method. I mean, form the characteristic equations and solve the equation directly using the common procedure. Okay, so you don't need to memorize any formula. Okay, any question from this example? If you don't have any question, we can wrap up this session, and after a 10 minutes break, we will start the tutorial session. Any question? Okay, thank you. So we will have a 10 minutes break, and after 10 minutes, I will start the tutorial. Okay, thank you.